Okay, so welcome back, everyone. We are going to finish up our discussion of nucleophilic acyl substitution today, and we'll talk about the chemistry of esters and also amides and nitriles. And one of the perks, I would say, of today's lecture is really we're only directly going to talk about esters and nitriles, because once you learn how nitriles behave by way of reactivity towards hydrolysis, you get amides thrown in for free, because it's actually quite astonishing. You're going along working on your nitrile and you're hydrolyzing it, and presto, all of a sudden you've got an amide as an intermediate. So if you learn the mechanisms for acidic and basic hydrolysis of nitriles, you automatically know the corresponding mechanisms for amides. That gets thrown in for free. Good. So we've already covered esters a fair bit. In this chapter, we learned that esters are one of the less reactive carboxylic acid derivatives, but they still can react with water. They still can be hydrolyzed. So again, that word hydrolysis coming from two Greek roots meaning loosening by water or something like that. And you can hydrolyze esters in either acidic solution or alkaline solution. We actually have talked about alkaline hydrolysis of esters back in chapter 27 when we talked about lipids. We said that you can take triglycerides and hydrolyze, or if you will, saponify them. And that now has in there the root that means soap forming. And so that's how soaps were made thousands of years ago already. Have one kid, at least in the other section, 513 at 1040, he seems very interested in soap making. So I think you can buy kits or something. I would say if you're really doing it from scratch, please be very careful. That does involve using strong alkali. So probably sodium hydroxide, which in concentrated solution is quite dangerous. It will burn your skin. And I don't even want to think about getting it in your eyes. So, but I would think as long as you use those nice, thick, long gloves, you know, that you use for cleaning things, and maybe some goggles, please, and just use your common sense, I think you would be fine. It's done all the time in chemistry labs, in even high school chemistry labs. So be that as it may, we're going to start off with that. I do want to remind you that we know of at least 3 good ways to make esters, besides Fischer esterification, which is one. We learned about that in this chapter. You can also make it by an SN2 reaction of a carboxylate ion that you would make by deprotonating a carboxylic acid. And again, you certainly could use sodium hydroxide or something like that, but you don't even need anything nearly as strong as that to deprotonate a carboxylic acid. Sodium bicarbonate or carbonate are more than strong enough. They will deprotonate it also, because carboxylic acids are fairly acidic. And then you would treat the resulting carboxylate ion with some alkyl halide, preferably primary. And Bella is just determined to get on YouTube today. You can say, hi, YouTube, to the whole world. Goodness. Okay, so, right, and so in that case, you'll just do an SN2 reaction, and you'll get the ester. That's another perfectly acceptable way of making an ester. And actually, I think it's just about the only way if you're making phenyl esters. So esters where the alcohol is phenol. The other good way of making phenyl esters is also the other good way of making esters, which is alcoholysis of an acid chloride. And generally, if for some reason you need to make a phenyl ester, that's what you would do. You would take an acid chloride and treat it with phenol, because phenol is much too acidic to work in a standard Fischer esterification type scenario. So, but those are the 3 ways we have of making esters. The Fischer method, the Fischer esterification, can be run in reverse by using, I shouldn't insult you and just read your class notes like that, but by using a large excess of water. And what you see here is the mechanism of acid hydrolysis of an ester, which you can certainly do. Hydrolysis of an ester, again, can be done in either acid or base. And if you look at this, I think you'll see that it's essentially the Fischer esterification mechanism, but exactly backwards. It's absolutely run in reverse. And that's because all of those steps are reversible. So this whole reaction scheme is reversible, can be run in either direction. How do you know which direction it will be running in? Well, you control that by the solvent. Remember that when we were doing, in fact, I should be able to call up Fischer esterification here. Remember that when we were doing Fischer esterification, here we go, we did that using the alcohol that we were condensing with the carboxylic acid as our solvent. And what that does is essentially exclude water from the mixture. Yes, you do get 1 molecule of water per molecule of ester that you make, but that molecule of water comes off and is immediately dissolved in this vast ocean of your alcohol. And so it's a non-factor. It's as if the water were removed from the reaction mixture. And indeed, there are ways there are variants on the Fischer esterification that use special glassware that actually literally remove the water from the solution physically. But even if you don't, it's still going to get driven forward due to being outnumbered by a factor of maybe 10 to the 15th or 10 to the 20th by these alcohol molecules. So it's as if you removed the water from the reaction mixture, and so you drive the equilibrium in this direction by Le Chatelier's principle. But all those steps are reversible. And here we go. Now we're back to hydrolyzing esters. And so if you want to run it in the other direction, then you want to do exactly the opposite. Instead of excluding water, you want to have lots of water around. And that's basically how you would do it. You would just add your ester to dilute aqueous acid. So it could be water with maybe a little bit of HCl or a little bit of sulfuric acid in it. And you'd heat it up. And now the equilibrium will go in the other direction. You'll drive the equilibrium towards formation of the carboxylic acid, the component carboxylic acid and alcohol. And once again, you will get a molecule of the alcohol, but that's going to be dissolved in this vast aqueous ocean over here. Again, the alcohol molecules will be so greatly outnumbered by the water molecules that they effectively don't matter. And it's as if you removed the alcohol directly from the reaction mixture. And there are probably ways of doing that as well. But again, even if you didn't, you've got so much water around that the equilibrium now favors formation of the component alcohol and carboxylic acid. So I just used ethyl benzoate as an example of an ester. I could have picked any ester. And when you practice your mechanisms, I recommend you do that very thing, that you make up your own starting materials. That's the best way to prepare yourself for doing mechanisms with starting materials you've never seen before. Or get with another student, make up starting materials for each other and practice mechanisms. Or as I'm fond of saying, get with your roommate, boyfriend, girlfriend, best friend, worst friend, mother, father, dog, cat, whatever, and have them, if they're able, make up molecules for you. So if you can get your dog or your cat to do it, I will be very impressed. I've been working on Bella for nearly 15 years at this point, 14 years, and she has so far shown no aptitude for organic chemistry whatsoever. Anyways, let's go over then this example, but I think we're already at the point in the term where everything starts to look real similar, one reaction after the other. And indeed, that's true. The further and further we get into the term, the less and less able I'm going to be to show you anything that will surprise you, that would be completely new. And by the time we get to chapters 29 and 31, which are going to be kind of the capstones in the course, 29 on metabolism and 31 on polymers, it will be impossible for me to surprise you. Every single thing we look at will just be applications of something we already know. So if you're beginning to feel that's a good thing. And another little known fact, little discussed fact, kind of taboo fact, is, believe it or not, that's when it starts to get fun. That's when you can really start to enjoy this subject, because you go, gee, here's another thing, but it's just the same as the previous thing. It's just another example of the same old, same old. That's when it really starts to get fun. And it does start to happen only about right about this time, about halfway through the semester of Organic 2. But it's well worth the wait. Speaking of being halfway through the semester, another thing I've neglected to mention is we're past the point in the term where this time last year, gosh, it seems so long ago. Seems like it's 10 years ago. But at this point last year was when we suddenly had to switch to online classes. So you can view my YouTube lectures from then if you want to see yet another version. I will give the caveat that there were things that semester that I said they didn't have to know because we ran out of time. For example, all of chapter 29, they were not responsible for, but you will be responsible because we are going to have the time. But other than that, if you just want, I don't know why you'd want another version of me doing the same lecture, but if you do, for some reason, I guess it's a slightly different format because it was non-concomitant. They were lectures that I made all by myself, if you will, and uploaded separately. Like, I guess I did a couple of lectures for you that way this term because of the winter storm. But those are available. You can find them from last year's material. Good, so we're in acidic medium. I think by now we're pretty used to looking to protonate our carbonyl oxygen if we're in an acidic medium and we're going to do any kind of nucleophilic acyl substitution, or for that matter, any kind of nucleophilic acyl addition like we had in chapter 19. And so the way we find out what we should use to put the proton on is, as always, by looking at what we're given. And all I've got is H3, all I'm given is H3O+. That means that all we have around are water molecules, mostly water molecules, with a few hydronium ions dotted around occasionally. Probably, no, not probably, definitely passing protons back and forth to each other. That process is very rapid. But it means that the only species we can invoke in our mechanism are going to be, besides that's inorganic anyway, will be H3O+ and water. That's all we've got. Those are the only other two species besides the organic substrate. So we'll use a hydronium ion to put the proton on our carbonyl oxygen. And now, just as we're used to seeing, now our nucleophile can attack. The already electron-poor carbon atom is now made even more so by being attached to oxygen with a full +1 charge. So it's all the readier to accept nucleophilic attack from a water molecule. Of course, water isn't the greatest nucleophile in the world, but in acidic solution, it's good enough. Certainly, we would not use a hydroxide ion here. That would not make sense. You can't invoke any strongly basic anions in an acidic medium, because you would be involving species, multiple species whose conjugate acids of pKa's are more than 7 or 8 pKa units apart in your reaction mechanism. And that doesn't make sense. You can't invoke species like that because they would never exist in even anywhere near an amount large enough that they could factor into mechanisms. And so the way we know that is, what's the pK of water? Well, it's about 15 or 16, right? Somewhere in that range. We're here in aqueous acid. We're maybe at pH 1, maybe 2, something like that. And if water is a pK of 15, well, we're 12, 13, 14 pKa units away. We're well over 7 or 8 pKa units away from the pH of the solution. So it does not make sense to use OH- when you're in an acidic medium. So we'll use a water molecule. That being accomplished, we'll get this tetrahedral intermediate. And you've already seen a number of times, this is the point where, if we're an acidic medium at least, we expect to have some proton transfers. And indeed, we'll first want to pull off this proton and the oxygen. How do you know that, and how do you remember that? Because if you did it in the others, these two steps in the other order, you'll wind up with an intermediate with a +2 charge. And I don't think anyone would find that to make a lot of sense. So instead, we'll first go to an intermediate with no charge, and then protonate the formerly alcohol residue ester oxygen. with using, again, a hydronium ion. And the reason we need to do that is because we need to lose our alcohol as the leaving group, just the reverse of the process of forming the ester. And we can't do that until you protonate it. You can't lose ethoxide ion in acidic medium. No way. Same reason as before. Ethanol probably is a pK around about 17, 18, somewhere in that area. And if, again, we're at pH 1, we're many, many, many orders of magnitude beyond where we can rationalize showing an ethoxide ion or any alkoxide ion in an acidic medium. As long as we protonate it first, we're fine. Then we can lose the alcohol as a leaving group. You could, of course, use either of the OH oxygens. They're the same. That now will float away very quickly. The wording of the question will make it clear what you have to put in where, what you have to show and where. Especially watch out with OWL, because they like making you fill in 7 boxes, including things with sodium ions and goodness knows what. So, so especially pay attention to OWL. In any case, once that's accomplished, you've essentially got the product. It's the carboxylic acid, except it's protonated at the carbonyl. So we'll once again use a water molecule. That species is the one that makes the most sense, that's most abundant, to pull off that proton, and you've got your free carboxylic acid. So that's how the mechanism of ester hydrolysis looks in acidic solution. And you wouldn't get a soap out at the end, but you certainly would be able to isolate your carboxylic acid. The alcohol, probably not so much. Yes, you do get the alcohol also, but seeing as it's 95+% likely that your alcohol is going to be either ethanol or methanol, those are soluble in water in all proportions. So, I mean, I'm sure there's some way industrially that they do that. If they, for some reason, want to get that alcohol back out, there's probably a way. And it probably involves multiple steam distillations and is probably a gigantic pain in the backside. It can probably be done, but in generally it won't be. Because both methanol and ethanol are, we say they are miscible in water, M-I-S-C-I-B-L-E, miscible, which means they're soluble in all proportions. So in practice, I don't think you're going to get your alcohol back out, but you could certainly isolate your carboxylic acid. That would not be difficult. Good, so everyone okay with that reaction in acidic solution? Any questions on that mechanism? But check it out. I think you'll be able to convince yourselves that it's essentially Fischer esterification run exactly backwards, exactly in reverse. What about basic hydrolysis or alkaline hydrolysis of esters, or saponification, as we also called it? Well, I think you'll find, as we so often do when we compare reactions that can work in either alkaline or acidic medium, that the corresponding reaction in alkaline medium is more straightforward than in acidic medium. There's fewer steps. You don't have all those proton transfers because you don't have to worry about avoiding minus charges because we're an alkaline solution. So again, here I've picked methyl hexanoate. I could have picked any ester, and I would recommend you also pick any ester when you're practicing this. But again, as we've seen time and again in alkaline solution, bombs away. You can just go ahead and do your nucleophilic attack on that carbonyl for your first step. In so doing, you'll get an oxyanion, an alkoxide ion, but that's okay. We're an alkaline solution. We're at maybe pH 13 or 14. So you can justify having that there. Even if we were to suppose that the corresponding OH, I guess that would then be kind of a hydrate, vicinal diol. But if we then suppose that OH to be the pKa of an ordinary alcohol around and about 18, it's actually probably quite a bit lower, but let's just say it's 18. Well, if we're even at pH 13, we're well within 7 pKa units. We're good to go. We can rationalize showing an intermediate like that in basic solution. Not in acid, but in basic solution, we're good to go. And again, next step is also very straightforward. We can just go ahead and lose our methoxide ion, our alkoxide ion as a leaving group. In basic solution, that's fine. Not in acidic solution, but in basic solution, again, we're fine. The conjugate acid of methoxide is methanol. Methanol, again, is a pK around 17 or 18. And if we're at pH 14, we're good to go. We can rationalize that. And of course, alkoxides are really terrible leaving groups. But again, in basic solution, it's good enough. So that's what will happen. And of course, I think the methoxide ion would very quickly pull a proton off of water and make methanol. And again, what you would have to show in terms of that will be made clear in how the question's phrased. Really, what we would most likely be going after is the carboxylic acid, since again, the great likelihood is that the alcohol portion of the ester is a small, miscible in water alcohol that we're not going to be able to isolate anyway. But the other piece is, of course, the carboxylic acid. And remember, we don't get to say we're done. We've generated that molecule in an alkaline solution. So again, remember, there is no way to prevent this from happening. It's gonna get deprotonated. And we could even use the same pKa rule. If this carboxylic acid, you figure its pKa is maybe 5, 4.5, something like that. Well, if we're at pH 14, that's well above the pKa of this. That's gonna get deprotonated. Can't be avoided. And we're going to, by the way, it's timely to bring up pKas and things like that, because we're going to be considering that tomorrow. It's so strange to say it, when we cover polypeptides and the various amino acid side chains. Good, so that deprotonation is going to happen. You cannot add the acid fast enough to prevent that from happening. If you did, you'd wind up with an incomplete reaction. So remember again, going back to numbered steps like this. Remember what that means. It means we add our ester to aqueous sodium hydroxide in this case, probably heat it a bit as well. Usually the heat's not quite as important with base as it is with acid, but you might or might not heat that as well. And so what's going to happen is it's going to keep reacting until nothing further can happen. And then that's when you add the acid. So we go through the whole saponification process. We get our carboxylic acid that will be immediately deprotonated by the hydroxide ion that's already in solution, and you will get the carboxylate ion plus, no doubt, the alcohol, and both of those guys will be swimming around quite happily in the aqueous solution until you acidify. And that's when the acid will, first of all, of course, neutralize any leftover hydroxide. That's pretty easy. OH minus plus H3O plus yields 2H2O. And once all of the hydroxide is gone, then it will start putting the proton back onto the carboxylate ion. And that mechanism is, of course, straightforward. That's just an acid-base step. You know about proton transfer steps. And so then you can thus isolate your free carboxylic acid. So that's how the mechanism of alkaline ester hydrolysis or saponification looks. And I haven't counted steps, but I'm quite confident if you compared this to the acidic mechanism, I'm pretty confident you'll find this is fewer steps, and certainly is conceptually more straightforward. That's, I just find that's in general the case when you've got reactions that can work under either alkaline or acidic conditions. So much for hydrolysis of esters. That gets us to 12:30. Questions on any of this? Please register your attendance, by the way. I do have a little quick assignment for you guys by way of our REEF attendance getting, but it will just be attendance today. I'll try to have a couple of polling questions for you guys tomorrow, if possible. I mean, I also don't want to burden you over much, but I'm aware that we've had 2 straight days of just taking, or did we do questions on Monday? Well, anyway, I'll double check and I'll see if I have anything for you guys tomorrow. Good. Well, I'm going to sort of blow through amides by pointing out what I did earlier. We're going to talk about hydrolysis of amides as well. But the thing is, if you understand the hydrolysis of nitriles in acidic or alkaline medium, then you automatically get amide hydrolysis thrown in for free, because those mechanisms are included in the nitrile mechanisms. So I don't see any point of going over them separately, because if you learn the mechanisms for nitriles, you already know how amides behave. I'll also remind you, both thioesters and acyl phosphates are important in biological processes. We will see cases of using both of those functional groups when we get to chapter 29, and spoiler alert, we'll find them both to be pretty similar to esters or acid anhydrides. So pretty similar reactivity, but we'll see examples of that, I would say, largely in chapter 29. Another thing we'll see in a later chapter, there's a section on step growth polymers, also called condensation polymers. And again, we're going to do a whole chapter on polymers. That's going to be the very last day of class. That's chapter 31. And again, all of you who are majoring in engineering or material science or something like that, you've been very patient all term. That last day is all yours. So you can enjoy that. That being said, I still want to bring up the idea. We already know that an acid chloride functional group will react with an alcohol functional group to make an ester. So what if we played a little trick on this whole system? What if we had some molecule, I'm just putting a box here, just to represent the rest of the molecule, but something that had two acid chloride functional groups and a diol, something with two alcohol functional groups. What if you reacted them together? Well, an acid chloride could react with an alcohol functional group and make an ester. Meanwhile, there's an alcohol functional group in the other side of the compound that can find another diacid chloride molecule looking just like this and react with that acid chloride and make an ester. There is an acid chloride on the other side that will find an alcohol and make an ester. This alcohol will find another acid chloride and make an ester, and on and on and on. You see where this is going. We'll get a polymer chain. This will keep growing arbitrarily long. Obviously not infinitely long. It will eventually end because you'll run out of materials. But you get a polymer that looks something like this. And I'm not in, I tried the best I could with drawing that. But that's what you'll get. This is sort of, and we'll talk about that when we actually get to polymers. You know, you can just sort of observe this for now. But I guess polymers will be fair game for the final exam, right? Because that's chapter 31. Well, again, of a couple chapters, just like an organic one, that I won't have examined you on yet. So they'll be fair game for the final exam. There may or may not be a slight emphasis on those chapters, but certainly polymers will be fair game for the final exam. So even though this section is in chapter 21, let's postpone all that and we'll cover all of it in chapter 31. But I wanted to give you kind of a foretaste of all that, just so you saw what all of that looked like. And we'll talk more in detail about how to draw structures of polymers. Generally, something like this is the best practice way of drawing polymer structures, where everything within the parentheses, we put this N here to signify that all of that repeats an arbitrarily large number of times. Could be thousands or tens of thousands or even millions of times. But other than that, one of the things we'll point out is there's many, many, many correct ways to draw the structure of any given polymer. I didn't have to put the square thing and then the circle thing. I could have started with the circle thing and then put the square thing, or anything in between. As long as everything's included within the parentheses exactly once, you're good. And like I said, we'll mainly focus on this in chapter 31. But I just wanted to give you a quick look ahead, since chapter 21 mentions all that. But other than that, I don't think we really need to concern ourselves too greatly with that right now. So here's the plan. I would like to spend the next, 5 minutes or so, 4 to 5 minutes, going over the mechanism of nitrile hydrolysis in acidic medium. And after that, although the corresponding basic mechanism or alkaline mechanism is on the next page of your class notes, I want you guys not to peek, because I'm going to give you the opportunity while we finish taking attendance to work that out on your own. So I'll do the harder one first, because again, I think it's fair to say in acidic medium, in general, the mechanisms are more complicated and are more steppy. It's still every bit as logical. It's just there's a bit more trouble to go through, at least I find, in acidic medium. So here we have benzo nitrile. I've just picked that compound because I felt like it. I could have picked any nitrile. And just as we would always protonate the carbonyl oxygen of carbonyl compounds in an acidic medium, well, now we don't have an oxygen, but we do have a nitrogen that can be protonated. And so we'll do that with our hydronium ion. At that point, our water molecule can attack the nitrile carbon, just as it would attack a carbonyl carbon. We've already pointed that out in chapter 19, that the carbon-nitrogen triple bond in nitriles is surprisingly similar to the carbonyl group in aldehydes or ketones in terms of reactivity. So that will attack and you'll get a species that looks like this. Here you're probably bracing yourselves for some proton transfers. And you'd be exactly right. We'll first pull off the proton from the oxygen because otherwise we'll get an intermediate with a +2 charge and you want to avoid that. This next intermediate will then of course get protonated so we can eventually lose our nitrogen in the form of ammonia. And there's multiple correct ways to draw this mechanistic step because that species is resonance stabilized. You could also draw it with a single bond to oxygen, double bond to nitrogen, and plus charge on nitrogen, for instance. And I think there's at least one other resonance form that is the plus charge in carbon. And remember, whenever you're looking at a resonance stabilized intermediate, you can in principle use any of those resonance forms in your mechanism. There will always be a correct way to show the mechanism, regardless of which resonance form you use. And actually, I'm predicting we're going to run into that a fair bit in chapters 22 and 23, probably especially 23, when we start looking at enolates. That's going to be a chance for enolates. They're going to be a resonance stabilized species. And I predict that I will say, I do not care which resonance form you use, whichever you prefer. It will always be possible to draw the mechanism correctly. Okay, so, but this is one way of drawing that protonation step, and I think it makes it the clearest what's going on. And then, if you look at this, you'll see that's nothing other than an amide, but protonated. If instead of starting with benzo nitrile, we'd started with benzamide in acid solution, well, the first thing we would do is protonate that carbonyl oxygen and we'd be here. So the rest of the mechanism is exactly the mechanism you'd get for hydrolyzing an amide in acidic solution. I should point out, of course, the amide doesn't have to be primary in that case. We're going to wind up with a primary amide here because we started with a nitrile, and you get first one and then a second hydrogen on that nitrogen. But if this were not a primary amide, if there are one or two alkyl groups replacing either or both of those hydrogens, the mechanism would be the same for hydrolysis. It's just at the end you wouldn't get ammonia, you'd get a primary or secondary amine. But the mechanism's otherwise identical, regardless of what's attached to this nitrogen, as you'll see when we move forward. So once you have your protonated amide, again, water attacks. We get attack of a second water molecule. We're going to get a second hydrolysis. Once again, proton transfers. First, we pull off the proton from this oxygen so we don't get an intermediate with a +2 charge. And then we'll want to protonate the nitrogen because we want to be able to lose that molecule as either ammonia or a primary or secondary amine. And we're not going to be able to lose NH2- or the equivalent with alkyl groups as a leaving group, not in acidic solution. No way. Ammonia has a pK of like 37 or something like this. We're here at pH 1. There's no way, no possible way you can lose NH2- as a leaving group in acidic medium. So that's why we need to protonate that first. Now we'll be losing a molecule of ammonia. This ammonium ion probably is a pKa around and about 9.5, something like that. And so if we're at a pH of 2, we're within 8 pKa units. That's close enough. We can rationalize losing that as a leaving group. Of course, ultimately, if we do get NH3, that's going to very quickly pick up a proton and become NH4 plus the ammonium ion. We don't really care. That's inorganic. And that's going to wind up, even if that were the conjugate acid of an amine, that's going to wind up in the waste jug. We're unlikely to be able to isolate that or interested in isolating it. But we do protonate that nitrogen using the hydronium ion. Then we can lose that nitrogen as a leaving group now that it's protonated. At that point, we've got our carboxylic acid, except it's protonated once again. We'll just use a water molecule, just as we did before, to pull that proton off and isolate our free carboxylic acid. So as I said, the basic version of this mechanism, or alkaline version, is on the next page. Don't peek, because I have such confidence in you that I think you'll be able to work this out on your own. So the reef grade you get today is, again, all just attendance. You don't need to worry about that. But let me see if I can get everything out of the way. I guess it is out of the way now. So where are we at? We're at 12:42. We have until 12:50. Let's go until, oh, I don't know, 12:45, 12:46. Well, that says 12:45 on that clock. I think that's probably close enough. So the challenge here is going to be getting all of these other windows out of the way. So let's see what we can do. And by the way, this is in your class notes also, which reminds me, I discovered there's probably a misprint on the 100-point attendance reef session we had the other day. I think I made mention of an aminolysis of an acid chloride, but it was using phenol. So that's not an aminolysis, it's an alcoholysis. So I'll try to remember to get up a corrected version of that. Well, let's put this down here for now. Good, so just like before, same old, right? Bombs away. You've got your hydroxide ion, which we certainly have present, attacking that nitrile carbon and putting the minus charge on nitrogen. It turns out that the conjugate acid here, once you get in other words, if you were to go from N- to NH, oh, I'm sorry. If you were to go from, a protonated nitrile is really, really acidic. Its pKa is like -10. And so we're here at pH 14. There's no way we would think of protonating the nitrile nitrogen first. So that's the point I'm trying to make. So hydroxide just attacks, we get this anion. I would expect that nitrogen to be a little better at bearing the minus charge than an sp3 hybridized nitrogen. Just as if you compare the pKas of ethylene and ethane, they differ by a good 20 orders of magnitude. I would expect to be the same here. Still, I would also expect that to get protonated by a molecule of water. Again, not H3O+, we're an alkaline solution, so we need to use only species that make sense. And interestingly, this guy actually already kind of looks like a carboxylic acid, right? It's sort of the cross between an imine and a carboxylic acid. But in any case, no surprise that this proton would be acidic. Hydroxide ion will pull that off very quickly. And as before, we get an anion that's resonance stabilized. You could also have pushed the electrons all the way through and put the minus charge on nitrogen. So double bond oxygen, single bond NH-. That's fine also. Either way, the proton's going to wind up on the nitrogen, and you'll get, lo and behold, hey presto, an amide. So from here on is how alkaline amide hydrolysis would work. And again, if it were not a primary amide, if either or both of those hydrogens were replaced with alkyl groups, that would not affect the mechanism at all. They would just be carried through to the end. So the mechanism is the same regardless of the type of amide. Again, we're in alkaline medium, so bombs away. Hydroxide attacks. We put the minus charge on oxygen. We're completely okay in doing so since we're an alkaline medium. And now we need to think a bit about charges. And as I put some thought into this, I really thought about this in recent years. I think in past years, I might not have been teaching this the best and most correct way. But I think now it makes sense to go ahead and protonate that nitrogen to give the plus charge. And we're totally fine in doing that, by the way. The pKa of this guy is maybe 9, something like that. And if we're in alkaline solution at pH 14, we can rationalize that. We're within the limit of 7 or 8 pKa units. But I guess if we put that proton on now, then the resulting molecule has a total charge of 0. So that kind of makes sense to do also, I think, in those terms. We can certainly then lose ammonia or whatever primary or secondary amine is a leaving group at this point, and you've just generated your carboxylic acid. Once again, an alkaline solution, and once again, you're not going to be able to prevent the hydroxide ion that's already present from deprotonating that carboxylic acid. And thus it will stay as the carboxylate very happily sightseeing around the aqueous alkaline solution until we acidify. And once again, the first action of the acid is going to be to neutralize any leftover hydroxide ion. And then it will start putting the protons back on these carboxylates to allow us to isolate our carboxylic acid. But exactly what you write and where and in what order, you know, that will be made clear what to do in the wording of the question. But certainly, I think this clearly shows how we get the major organic product out of this, which will be the carboxylic acid. So again, I think conceptually real similar to what we had with the acidic medium, but we're just working on the alkaline side. And so we're avoiding any highly reactive cations. Good, but I think that's about it. I can't really think of anything else. Well, I can actually close that out because, as I said, it's here in your class notes. So any questions on that mechanism? Class is silent partners today. All right, well, it's 12:50, so I need to let you guys go. But remember, I will see you tomorrow at noon. So tomorrow, don't go to your Thursday classes. Go to your Friday classes, including this one. And then we'll have Friday off. So we'll see you all tomorrow then. Let's see, we can close this down. Stop recording.